Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, so this is part of the Microsoft Quantum Center for Computational Thinking, which is really about, how we can apply ideas, how do we think differently in computer science, and what's the approach to computational take. And we started by Jeanette Wind, and her theory was that there's really a set of techniques which are quite particular to computer science, and to see how they, what they are, things like recursion and the use of abstraction in more prevalent ways. And so this parallel thinking is really about what are the main ideas in parallel. If we want to go to parallel computing, what should we be doing? Of course, the motivation for this is parallelism is becoming prevalent. In scientific computing, people have actually been using parallelism for a long time. But in everyday use, for all of our students and everyone in computer science, now everyone on their desktop is getting parallel machines, and this is increasing exponentially. This slide is actually from Andrew Chen, and so he's basically predicting that by 2015 we're going to have 100 cores on our desktop. Andrew's the vice president at Intel. So I'm not sure if we can hold him to this, and it might not be exactly the right number, but this is sort of a trend at least, exponentially increasing. And of course, there's not just parallelism in multi-core. There's parallelism that we're all going to use, ubiquitous parallelism, in the fact that we all access various services on the web. Many of those are running in parallel, whether we know it or not. Every time we do a search nowadays, that search is going to run on lots of different machines, and more things are going to run. And furthermore, there's a recent trend, which Microsoft is also involved in, which is actually allowing people to download their own applications on these sorts of machines, parallel applications. And so, these are basically truckloads full of servers, right? I think two of these are actually Microsoft. This is Microsoft's conceptual idea that's actually that's competing. So everyone's going to have to deal with parallelism, because everyone's going to have a parallel machine on their desktop, and in order to get any sort of improvement in performance over the next few years, and the clock rates are going up, we're going to have to deal with parallelism. So what are the problems in moving to parallelism? Well, there's all the standard ones. We're going to build hardware, but that's already happening. In fact, I just showed you some of the previous phases. We're going to have to develop good programming languages. Well, there's been a lot of ideas in the last 20 years in this, and I think we just have to put them together. Developing efficient parallel algorithms. There's also been a lot of ideas here, and in particular, I think the scientific computing community has contributed a lot to this. Good compilers, OS support. So there's all these things, but at the end of the day, I think this is the most problematic of all of them. Right? Moving forward, it's educating people in parallelism. And we do a very bad job of it. We currently, all of our courses are very much concentrated on teaching what I call sequential thinking from the very first data structure courses. And what this leads to is sort of a way that most people think about parallelism is as a set of communicating sequential processes. So this is the way that most people attack parallel problems. Is it's a natural thing to do in NPI. You've got a bunch of these sequential processes. They send messages to each other. You get these very complicated algorithms, and it becomes an extremely difficult task to do rather simple things. Similarly, in threading libraries, you think of building a bunch of threads, and they communicate maybe through a shared memory instead of through message passing. And MapReduce sorts of paradigms improve on this, but without going into it, I claim that they still narrow your mind the fact that you've always been thinking sequentially. This is because people learn how to program sequentially. They think about it. They always approach something from a sequential way of thinking about it. So the idea of parallel thinking is that basically parallelism is that we want to basically not think about it as we want to basically rethink how we're going to do things. Right? So we don't want to brainwash students into thinking sequentially. And in particular, we want to sort of identify a set of core ideas that we can teach our students about what parallelism is. And what I mean by core ideas here is not interfaces like MPI. This is how we typically teach parallelism nowadays. We have special courses in parallelism at the end of the curriculum where we basically say, okay, now we're going to look at some parallel libraries such as MPI or maybe CUDA or maybe MapReduce, etc. And we basically get a very narrow focused idea rather than thinking about parallelism from the top. So basically the claim here, the conjecture is if done right, that at the right level of abstraction, programming parallelism can be just as easy as sequential programming. And then the idea is, what are the core ideas? So what I'm actually going to spend the next 20 minutes on is trying to convince you that parallelism is very easy, and I'm going to show you a sort of things that you could teach a freshman in computer science, and that we should all know, that everyone should know about parallelism. And if you're in parallel computing and you don't know this stuff, then you should. Okay. So I'm going to start with a simple example, which is quicksort. This code is actually from a 30-year-old book. 78, in fact, I think the original version of this book was 74, so it's 35 years old. A.O. Hoffman-Algorithms, it's an algorithms book, and they weren't designing parallel algorithms at all, because it was back in the time of sequential. But what's sort of funny about this is that this description is actually much more parallel than anything you would find in a current textbook on algorithms. And in particular, we teach quicksort's a good example because it's something we teach pretty much all of our freshmen. Covered in just about every freshman course that's across the country. So the description here is basically you pick some elements from a set. You call that the pivot. You find these elements which are less than that, the ones which are greater, and the ones which are equal. And then you recursively sort the ones which are less and the ones which are greater, and then you put them together in some sort of order. Okay, there's a huge amount of parallelism in here, I claim. Some of it comes from the fact that we can make these two poles parallel. And if you look at this description here, it's not saying anything about the ordering of execution. It's saying how we put things together. So if you think of this as a declarative description, there's no reason we can't apply these two quicksorts in parallel. It doesn't say I first have to execute this one and then that. In particular, you can't execute these in parallel. But there's another source of parallelism here, which is we can pick the elements less than, equal to, and greater than the pivot. We can compare the keys to the pivot in parallel. Right? So we can take all of our keys and compare it to the pivot in parallel and pick out the ones which are less than, equal, and greater than parallel. And in fact, there's a huge amount of parallelism there because we have a large number of keys and we can do the whole comparison in parallel. So at a high level, there's a huge amount of parallelism here. And when we teach quicksort, it's very important that the students understand this. The current way we do it, they're clueless that quicksort is a parallel algorithm. Now, if you have experience with parallelism, you probably know it's a parallel algorithm, but even then, my experience is most people that deal with parallelism still don't really have a sense of how much parallelism is in an algorithm like quicksort. And one thing about this is that by raising the level of abstraction, I actually claim this description is a much higher level of abstraction than what's given in most current algorithms textbooks, which gives some sequential loop about maybe starting at the two ends and swapping to find them. You actually you expose the parallelism of this algorithm. So part of this is we need high level descriptions, and we need to revert back to the core ideas of the algorithm. So this is really the minimum description of quicksort you need to get the idea across, and because of that, it ends up being parallel. If we start going into lower level details, we end up sequentializing. And there's a large lost opportunity not to describe parallelism. This really should be described at the beginning. So here's actually a piece of code for quicksort in a language called Nestle, which is a language I developed a long time ago. The point here is that you can put this in a concrete syntax, not just in a pseudocode. And this, in Nestle, wherever you have curly brackets, it means parallel. Now, of course, part of the goal in teaching algorithms is being able to analyze them and be able to compare them. So when we teach quicksort, the whole reason we do it is we say, well, this is better than insertion sort. And we say, well, insertion sort runs in order n squared, time. Quick sort, we can analyze it, and it's order n log n, expected time. And so we would like the similar sort of idea in the parallel sense. We would like to be able to compare two algorithms and say, well, how parallel is one compared to the other? So I claim that this is also relatively easy to do. This is all stuff that should be easy to teach parallelism. And the way we're going to do it is, in fact, we're basically going to just keep track, when you have a piece of code, of instead of one measure in sequential analysis, we just keep track of sort of the runtime. We can keep track of two measures, which I'll call the work. And the work is actually exactly the same as the sequential runtime. It's just the total amount of work done by the computation. And the span. And the span is basically the longest sequence of the sequential dependencies. And it's actually very easy to calculate. When we make parallel calls, like in this quick sort here, we basically just take the maximum span of any of the recursive calls. So this quick sort, I'm making two recursive calls in the less and greater elements, and we take the max of the two. And it's a very simple rule, compositional rule, to calculate the span. And it turns out by calculating these two, there's a whole theory about optimal schedules. You can prove various things about you can then schedule this efficiently as long as you have no more processes in the parallelism. Parallelism is the work over the span. So this, by dividing the work by the span, you have a very good sense of how many processes you can make use of. Okay, so clearly the higher this ratio is, the more parallelism is. And so we can just quickly look at quicksort. If we look at the completely parallel quicksort, it turns out that the filter operation, that's where we pick all the elements greater or equal to the pivot, is about log n depth. We actually have to pack, after we decide that they're less than the pivot, we have to pack them together, and the ones which are greater, we have to pack them together, and that takes a certain amount of depth to do it. I'm not going to go into detail. So that takes log n depth, and then we can make two parallel calls, and because we take the max, they can run in parallel. So the span of the algorithm you can sort of show schematically in this way is basically going to be log n, and then there's the depth of quicksort is log n, the recursive depth is log n, because it's basically divided approximately in half at each step. So the total span is log squared n. The depth of this computation. The total work is, well, we already know what that is because we've all learned that in our intro class on algorithms. It's n log n expected. And the parallelism, like I said, is just dividing through. So this means we can take the use of about n over log n processes. So it's actually a very parallel computation. If we were sorting 10 million keys, we could take advantage of about 500,000 processes. It's more than we'll ever have. So it's not saying we need that many processes. We can actually run this on one processor, 2 or 4 or 8, but we could use up to, this is all with big O, not exact, but we can use quite a few processes. So this is a very parallel algorithm. It's a relatively simple way to analyze it. And again, I think this is something, I have taught this to a lot of students, and I can teach this in one lecture, basically, easily, less than one. Now we might ask, well, what if we don't? We make two sorts of parallelism. We make the actual selection of the elements less than greater than equal to the pivot. That's done in parallel. We do this giant comparison. We also make the recursive calls. Now you might say, well, what if we just take advantage of one? In fact, this is most parallel quicksorts I've seen out there written in papers, including some of the Microsoft papers on parallelism, do the partitioning sequentially, and then they make the two recursive calls. So this is picking the elements less than the pivot, for example. And you can then analyze the span doing it this way. Well, just this partition here is going to take order n time, right? And then you make these calls happen in parallel. You can analyze the total span. It's going to be order n. Basically, because each one of these is about half as long, and the total thing is order n. Then you can divide through to get the parallelism. The parallelism here is only log n. So this says we can make use of about log n processes, which for a million keys is about 20. And in fact, because of overhead, you probably only get to take advantage of 10. In fact, our experiments show that for a million keys, you really start running out of parallelism at about 4 or 8 cores. So you've got very limited. So anytime you see a piece of parallel code that does quicksort, does the partition sequential, which most versions I've looked at do, and then make parallel calls, basically you're good for up to about 8 cores, and then you'll be in trouble. So it's not a very good parallel algorithm, but this gives you a nice way to understand the parallelism of this. It's very much less parallel than the previous one. And the funny thing is that if you do it the other way around, that you parallelize the partitioning, in other words, I compare all the keys to periods in parallel, but I make my 2 recursive calls sequentially. So, first call one quicksort, and the other after the first one's done. I actually get stuck in the exact same realm, and I end up with a span that's again ordering. So it's sort of interesting that you really need to take advantage of both of them, otherwise you're extremely bad parallels. So these are relatively simple ideas that most people, even who've done parallel programming, don't understand that something simple like this. So there's lots of other algorithms we can analyze. Here's a recursive matrix multiply. We can do the work is order n cubed. It's a standard matrix multiply. You can do the depth as log n. So this is an extremely parallel algorithm. N cubed over log n. Parallelism. More processes we can ever make use of. We can analyze his matrix inversion using the so-called Schur complement. This is basically the block Gaussian elimination. So we do a whole block of Gaussian elimination, make a couple of recursive calls. The parallelism here, the work is order n cubed again, and the depth here is actually order n because there's a sequential dependence between the 2 recursive inversions. And but the parallelism is again order n squared, so there's a lot of parallelism. Fourier transform. These are, by the way, these are actually pieces of code. This is the whole nestle code for Fourier transform, FFTs. So in Fourier transform, we know it's a simple method. It's a recursive method where we basically do a Fourier transform of the odd elements and even elements and put them together. This is the Cooley 2-key algorithm, which apparently was actually invented by Gauss. And again, it makes 2 recursive calls. They can happen completely parallel. Furthermore, the selection, all the multiplies and adds, when you put things together, can be done in parallel. So the depth of this algorithm, or the span of this algorithm, is log n, because we basically get a huge amount of parallelism, both from recursive calls and because of work in each level. So you get work in log n, which is the standard sequential runtime for FFT. Depth log n, so we get a huge amount of parallelism again. So it's relatively easy to analyze. Now you might say, well, MapReduce, there's a lot of hype about MapReduce. So we don't worry about the implementation niceties of MapReduce. So what really MapReduce will give you is fault tolerance. But from a programming point of view, this is all of MapReduce reduces to about 4 lines of code. So this is, again, this is Nestle code that implements sort of MapReduce framework. And so map is actually built into that. So the curly brackets in Nestle means we'll do for every element some operation. And then you collect up all the values on a particular key. So you collect up the results. You say for each pair, you do the collection. And this is for every pair. And this collects all the elements by the key. And then you do some reduction operation. And it's a relatively easy thing, and I think we can teach it again to students. And here's the standard example that's used for, as an example for MapReduce, where you basically count the word count. You've got a bunch of documents, you want to count how many of each of the different words are in it. And so we've got the map function here, and a reduce function here, and a set of documents. And this comes through in MapReduce. And we can calculate the work and the depth of the So these are all basic ideas. I've got a couple more here, which I'm going to skip because we're running out of time. We can do parallel prefix, which every element sums up everyone before it. This is something that seems extremely sequential. This actually can be done in a few lines of parallel code. So this, again, this is the complete code for it. And so every element gets the sum variable before it. We can do merging. This is something that we always teach. Again, here's an example of where we sort of brainwash students into thinking about merging being a sequential thing, where we start at the two heads of an array or a list, and we pull one element off at a time. Many people, even people who've done a lot of parallel programming, don't realize merging is actually very easy to parallelize. And there's very simple algorithms. So merging is you've got two sorted lists, and you want to you basically want to generate an output of a single sorted list. And this can be done in a simple divide and conquer method. I'm just going to skip through it, but again, this page along with this page is the whole code for it. This one does some split operation, basically binary search to find the middle one list and the other list, splits them together. Okay, so let me just sort of finish off by listing what I think is sort of core ideas in parallelism that we could teach to freshmen. We should be teaching right from the start. So first of all, all the parallelism I've described here is what I refer to as deterministic parallelism. So independent of the order of which things are executed, you always get the same result. I think to start teaching parallelism, this is extremely important. You don't want to be dealing with race conditions and non-determinism which comes from it. That's an advanced topic that should be taught at some point, but not at the beginning. That it's very easy to sort of analyze, you get a rough sense of the parallelism by doing this work and span. That you can look at the quicksort, for example, you analyze the work of an algorithm and span, and then divide them through the two of them and get parallelism. Divide and conquer is a very naturally parallel thing to do. Every student should know this, and they should be able to analyze algorithms by using work and span and analyzing. Furthermore, a lot of things which you don't do in divide and conquer sequentially actually end up, you can get parallel algorithms by divide and conquer. So the example of merging was something that typically we don't use divide and conquer, but if you want a parallel algorithm, then you are going to switch to divide and conquer. Then there's a bunch of other techniques. There's contraction. The scan example uses a technique called contraction. I don't go into much detail, but the idea is you solve a problem that's smaller and use that to solve the bigger ones. Another standard thing is there's a lot more heavy use of trees instead of lists. You don't want to use linked lists in parallel algorithms because then just chasing down the linked list is going to be very expensive. So there's a lot of sort of changes in what we would do. Now, at the top level, what we would teach in a sort of data structures course, an introductory level, at the first year level, isn't that much difference. We would still teach divide and conquer, we would still teach quicksort, we would still teach merging, we would still teach graph algorithms, we can still teach keys or matrix algorithms if that's what we want. But some of the details are quite different, and it's important to sort of think about how we do this and what we want to be teaching in a course like this. Okay, so that's the ideas. I have some slides on locality. I'll skip that. Couple minutes. Okay. The last thing I wanted to mention, which is actually more the research I've been doing, is one thing about parallelism that's been extremely difficult, and I would say is one of the hardest nuts to break, is to deal with locality. So every parallel programming paradigm has a different way of dealing with locality. MPI is, well, you break things up into processes. CUDA, you break things up by local computations, and it's always very hard to deal. So if we want to be teaching parallelism at this very high level I just showed, like this quicksort, one of the complaints I sometimes get is, well, that you're not dealing with communication, etc. I think it's extremely important for the community as a whole to come up with very high-level ways of discussing locality parallelism instead of these very low-level mechanisms, which basically involve splitting things up among processes and then communicating them or splitting them on threads. Or there's lots of different ways that different programming models give you to think about locality, but they're all very low-level ways. So I think this is actually an open problem. It's a problem that I've been working on actively, which is coming up with high-level notions of locality so that we can, for example, look at that quicksort as I wrote it and answered the question, well, how local is that? It turns out that quicksort actually has good cache effects and good locality because of the way that it scans on each pass the array sequentially ordered. So it is it's not the most local sort of sorting algorithm, but we should have a way to do it. And so I've actually been working on some papers on this topic. I don't have time to do it, but I do think this is an extremely important topic to look at a high level. In fact, just quickly, if we look at this block matrix multiply here, which I mentioned is extremely parallel, because we could make it 8 recursive calls to matrix multiply in parallel. I think I mentioned the span of this algorithm is log n. It's actually also got extremely good locality aspects, because we keep breaking down the problems into blocks, and it ends up having as much locality as a block matrix multiply would have. So we would like to be able to some high-level way of capturing this locality, and so that we can describe it without going into low-level details about the machine. Okay, so conclusions. Educating programmers on parallelism is key, and furthermore, I don't think the right approach is to teach sequential computing and then tack on parallelism at the end. I think this sort of gets people thinking about the wrong way. Another thing is to identify what the core idea is. I tried to do this in the context of a introduction data structures course, but it should be embedded throughout the parallelism. And another notion is to separate parallelism from concurrency. This is the idea we want to separate, keep away from race conditions and non-determinism at the beginning, and at some point we have to introduce that, but we're going to keep them clearly separated. Like I say, we should be able to teach parallelism from day one, and I think this is an important thing to do. I've actually been working on a freshman level course.
Thank you very much. Does anyone have any questions?